Okay, so let's continue to our topics that I was supposed to teach you. First order systems. First order systems. So the first order system I'm teaching you, they are stable systems. And actually you had to guys, please mute your microphone speaker. So they are written from ME430 that you have to pass before coming to this course, and with the closed loop transfer function of tau s plus 1. But I know that the majority of you didn't pass the course. I'm going to just give you an overview how we derive this. So as you see here, that the first order systems, they have one pole. So the pole of the system is in the 1 minus 1 over tau. So if you plot this real and the imaginary axis in the S-plane, so it's going to be here. We are showing the pole that I told you about the cross. Say minus 1 over tau. Okay, so we see because it's in the left-hand side of the complex plane, so the system is stable. So the trivial example of this is the spring and damper that you have seen in the, or you will see in the vibration course, ME530, K and the C. And then you have this force, external force or input to the system, KFT. K is the same. This is the stiffness. I'm just multiplying the force by stiffness, a constant number. And see the damping coefficient, that's right. And you know that for deriving the differential equation of this, you cut from the system here. When you pull to the right, so there's a resistant force, force of the spring, Fs, and the resisting force of the damper, Fc, damper. Okay. So, and using the Newton's second law, sum of the forces in x direction, say here is the x direction, is mx double dot. Right? So do you see m here? Do you see a mass here from Newton's second law? Do you see, guys? Yes or no? No, so this is 0 because there's no mass. So only acting forces. Acting forces are K F of t minus Fs minus Fc, because here is positive, this side is negative, from ME220, that's right, dynamics, is 0. And we know that Fs, linear spring force, is the stiffness of the spring in displacement, Kx. And for the linear damper, it's Cx dot, velocity in the damping coefficient, and this is 0. So simply you have Kf of t equals to Cx dot plus Kx. What I'm going to do, I'm going to derive this first order system in this format of transfer function, closed loop transfer function. So if you apply the Laplace transform, and knowing that the initial value of the displacement and the velocity at time 0 is 0, so what you get from here is C Laplace of x dot, as I taught you, is S x of s. by expecting this, plus k x of s. Now we are going to frequency domain k f of s. So x of s, you can factor out, is cs plus k is k f of s. So the output of the system, this displacement of spring and damper, over the input of the system gonna be k cs plus k. Here we go. Oh my god. Right? Yeah. Okay. Clear, guys? So what you want to make it to this format. So you say x, I'm dropping s because we know that in the frequency domain, x over f. You can write it like this: k over k, c over k, s plus 1, right? I'm just factoring out k. Now this k with this k goes to hell. So x over f gonna be 1 over c over ks plus 1. Now I can name this as tau, which tau, and I'm gonna write as this tau s plus 1. Here we go. So you can model the spring and damper as a first order system. For the people that you're passing ME430 with me, what's the name of the tau? What's the name of the tau? Or we passed tau? If I passed ME430? What's the name of tau, guys? Do you know in the mechanical engineering or control engineering? Yes, it is time constant. Time constant. Time constant of this first order system. Can I go to the next page? Oh, sure. No problem. So, having output over input in S domain is 1 over tau s plus 1, okay? So, guys, hold on please. Hold on. Sorry, it was a noise. So, now our mission is to see how the system behaves by implementing different inputs. The first input that I'm gonna do is I say f of s is 1. So what does it mean in time domain? What was the time domain input that I applied? So it means f of t was how much? Delta of t. What is delta of t? Impulse, exactly. So for the first order system, I'm gonna only teach you this system, not the RC and the fluid of tank of fluid, because you have to learn this in the ME430. So I'm just giving you the example of this, okay? So having this, f of s is 1, so you add x of s is 1 over tau s plus 1. Or you can write like this, guys. You can write like this, 1 over tau S plus 1 over tau. And we can write like this, 1 over tau S plus 1 over tau. Why I'm doing that? Because I'm going to apply Laplace inverse, guys. Laplace inverse. To find what? To find x of t, subject to input as the impulse. So which function gives you such a transfer function? I taught you. 1 over tau. So you know that Laplace of e minus at is 1 over s plus a. You have in your notes, that's right. So it's going to be exponential e minus t over tau. So we found the solution of the first order system generally by this specific example when the system is subject to impulse. So if I want to plot it, and we're going to do in the Simulink together, okay, for the first order systems, after teaching the old inputs, so t and the x of t. At time 0, x is going to be how much? Time 0 is going to be 1, is 1 over tau. So say here, at time infinity, x is going to be how much? If you put time infinity, this goes to 0, it's going to be 0. It's going to be 0. So you are going to have this. Here we go. So you see that this is the input to the system, impulse. Huge. This is input. This is impulse. And this is your x. You see that your output follows the input. By saying that, if you plot the block diagram for the first order system like this, and now you know how to do it in the Simulink, that's right. So here is delta of t in time, and this is x of t time. So you know that there's a unity feedback, and the plus minus, we have done this in the Simulink in the previous class. So what we're going to put here, you tell me. Closed loop or open loop transfer function? You tell me. Open loop, g of s. So how to find it? I told you several times. X over f, this is closed loop, is 1 over tau s plus 1. For finding the open loop, we're going to put g for unity feedback, is 1 plus g, that's right? So if you do this, you find g of s, the open loop transfer function for the general first order systems, is 1 over tau s. So you're going to put here 1 over tau s. 1 over tau s. So what's the name of this signal I taught you in theory and Simulink? Output being compared with the input. What's the error signal? E of s. So your output follows your input. Saying that means your error signal is how much? Error signal is how much? At the steady state error signal is x of s minus f of s is 0. Yes, guys? Yeah, please go ahead. Yeah, I'm just putting, yeah, you're right. So I'm just putting here because I'm talking about the steady state in time domain. You have to put x of s here and the f of s here, obviously. Yeah. Can I go to the next page? Yes. Okay. So to validate this, based on whatever I taught you, you can use final value theorem. Oh, yeah, ESS. Steady state error signal is a limit of s f of s input to the system 1 plus g of s when s goes to 0. So you know that the input is impulse, so it's 1, and the open loop transfer function g 1 over tau s when s goes to 0. Put the s0 here, 0, obviously. Okay? But I told you that for the first order system, this is general solution in time domain. And we name this as a time constant. So why we are naming as a time constant? So let me give you two examples. Say you want to have x1 is 1 over 2 e minus t over 2. Your time constant is 2. And the x2 is 1 over 10 e minus t over 10. The time constant is 10 seconds. Or whatever. Okay? So if you want to plot this, if you want to plot this, okay, t versus x. So this is gonna say, I'm gonna plot this first, this one, next one. At time 0 is, say here, here's 1, 2, like that. That is 0.5 and then goes to 0. 1, 2, see, because at t equal to it, it's becoming very small value, see? Here we go. But for the other one, it takes 10 seconds to become the same e minus 1. So you're going to have this. It's going to come here. And it takes much longer time until it goes to 0. So this is slower to settle down than this. This is slower than this. Understand? Yes, guys? Huh? So we can try this in the MATLAB before going to step. Because I told you that the x of s over f of s is 1 over tau s plus 1. What we don't have in MATLAB coding, I told you, we don't have what? We don't have impulse. So what I'm going to do, I'm going to play with this for the first order system. I'm going to say, because this is 1 impulse, we say that 1 is 1 over s. It's going to be 1 over tau s plus 1. I'm moving this s here as we did in the previous class. So x of s going to be s tau s plus 1. But the input going to be what? You tell me. What is this? What is this? What input is this? I taught you. Go to look at table. Yes, step, because MATLAB has this in the coding, step function. So I changed the closed loop transfer function from this to this, but with the step function. It's going to give you the impulse. Okay, let me go to the MATLAB before going ahead in mathematics. Do you agree? So I'm gonna send to you, okay? Or it's the code. Pause this. I can say, so by having different this, you can have your numerator, okay, you can. Your numerator gonna be 1 and 0. That's right. 1 is coefficient of this plus 0. And the denominator gonna be tau and 1. That's right. But the original one, numerator was different. That's right. Original one was 0 and 1. See the difference between them, this and this. Okay. So let me go to MATLAB. Oh, we have here from the previous class. I just have to change the name. So so it was, num was here, 1 and 0. So I'm gonna plot two with different time constant. It's gonna be with time constant of 2. Look at here, guys. Time constant, I'm gonna put 2. And another time constant, I'm gonna put 10 of 5. See what I'm saying? So for 15 minutes, step function, then 1, and then I'm gonna say hold. Now you know the hold command is right. And step as then 2. And I'm gonna just change the title to impulse for first order systems, right? First order system. Impulse first order. So if I plot this, let me save this here. Impulse first order. Okay. So 1 0 2 1 5 1. That's right. If you run this, here we go. See, this is impulse, exactly as I plotted, right? Comes on. We need more time. So see, for 5 seconds, see, takes more time. That's the meaning of physical meaning of time constant. So I have to increase this to 30 seconds. Okay, and I can say here legend here is for tau equals to 2, and the other is tau equals to 5. That's right. Now if you run this, here we go. Here we go. Yeah. Do you see this? So, oh my God. Okay, so see that? Is time constant of 2 for impulse, follows the input, and for increasing time constant, it takes longer time to settle down to 0. Understand, guys? But we reshape the transfer function to have the impulse response, because the MATLAB has no such a command. And now, as we are here, I can do rapidly for the Simulink. Bear with me that I can do and also upload it to you. and see what's happening. So I'm just commenting here, larger time constant takes more time to settle down. You can have it. Okay. Okay, our block diagram.
Is that
Yeah, arbitrary function. So you say, I don't know, give me a number, whatever you want. You can say one and two, whatever. Okay. So I'm selecting this from previous class. I'm gonna send to you. Okay, again, don't worry. I'm generating a new one. I'm just copying here. Okay, we got it. So say bye bye to this. And so you see that we have to just only change the transfer function. Open. Okay, guys, as we did in the previous class, let me first do it. Okay, guys. Now our new transfer function, let me go back here because I'm teaching you the first order system generally. So your first order system x over 1 over s for having the impulse input was s and tau s plus 1. Let me stick to example of tau is 2, that's right, because it's a numerical in Simulink. So now you have to find your open loop transfer function for the Simulink. See, for the MATLAB coding, guys, you have to put what? You have to put the closed loop transfer function. But for Simulink, you have to find open loop transfer function, G1 plus G. So it's going to be S1 plus G, G2S plus 1. So it's going to be S plus SG, going to be G2S plus 1, or S equals to G2S plus 1 minus S. So you see that the open loop transfer function that you have to implement in the Simulink block diagram gonna be S divided by S plus 1. Bingo. This is that you have to put in the Simulink. Not this. Not this. This is closed loop. Closed loop in the coding, open loop in the Simulink. Okay? So this is your... Yeah, sure, go ahead. Take your time. Oh yeah, there we go. No worries. When you are done, let me know. Yeah, I moved to other side. So I just moved this to other side. Because if I don't do that, maybe other students, they're gonna say what happened. Okay? See what I'm saying? So you saw that now for the open loop transfer function, so num is 1 and 0, you're then gonna be 1 and 1. There is a change in the denominator. Closed loop is tau and 1, here is 1 and 1. Okay? Here that was 2 and 1, here's 1 and 1. So can I go to the Simulink? Okay, so having being said, so you see that you have to have the same response. So I'm just double clicking on this, so it's gonna be, this is a stable system, one-on-one, one-on-one. See, numerator 1 and 0, one-on-one, exactly as I wrote here, one-on-one. So I'm just applying this and saving this, and error signal, obviously a copy and paste. I put it here for the error signal, okay. And this is our, and I'm saving this for sharing with you, impulse first order system. Okay, you see that it changed to S over S plus 1 as our transfer function, open loop transfer function. So guys, I'm emphasizing, when you're coding in MATLAB, you have to put for step response, as you're gonna see eventually on the parabolic response or the ramp response, you have to put closed loop transfer function. When they come to simulating, you have to put, you tell me what? Open loop transfer function. Let me double check this, everything right. And now I'm gonna say this to 15 seconds and run it. Here we go. You have to have impulse response, even if that you have step input here. Exactly. Okay, here we go. You see? As we had in the MATLAB code. And obviously, error signal must go to 0. What? Oh, it probably must back to that. Okay. Just worried about this, guys. Okay. And I don't want to plot this because I don't care about this. I'm saying that way. This is from a previous example. Okay. Right click. This. Okay. All done. Okay. Now I can have better vision. Yeah. See? Okay. So we have it. I'm gonna send this to you. And now I can, let me put it down here. Let me go back and continue the topic with B. If the input to the system is 1 over S this time. What's 1 over S? Means that f of t is how much? Unit step. So we are done with impulse. And let's go for a step. So x over f was 1 over tau s plus 1 for the first order systems. Guys, before going ahead, this is also a first order system, so I'm gonna teaching in detail in ME430. RC circuit is a first order system. This is also a first order system. This is H, tank of the water or any fluid. Here is the resistance of the tank, capacitance of the tank, out flow rate, in flow rate. These are the first order systems along with the spring and damper. I'm not covering here because I'm supposed to teach in ME430, but these also, they have the same transfer function, the first order transfer function. See what I'm saying? Yes?
Yes.
So, but having said, get that the x of s gonna be 1 over s, 1 over tau s plus 1, because your f of s is this. From a high school, you know, you can decompose this to as a over s plus b over tau s plus 1. And obviously, you know how to, the simplest way to find the a and b, you have to say a tau s plus 1 plus bs is s tau s plus 1. So this gonna be equal to how much? How much? 1. So if you do that and factor out s from here, you're gonna be a tau plus b is 0 because 1 has no s, and the a is 1, obviously. A is 1. So if you implement this here, I'm gonna go to next page. Please let me know if you're done. Okay. So and the a tau plus b is 0. So a is 1, so b gonna be minus tau. So your x of s gonna be 1 over s, a is 1, minus tau, tau s plus 1, or 1 over s minus 1 over s plus 1 over tau. If you factor out tau, you get this, obviously. Clear? So the solution in time domain, what you gonna do? You tell me. You tell me. Laplace inverse. So you get x of t. What's the Laplace inverse of this? Come on. Which function has 1 over s Laplace transform? Which function? Which function has 1 over s Laplace? Which function? Which function? Guys, can you? Yeah. What? You don't see I'm circling here? Which function has Laplace transform of 1 over s? Let me change the color, maybe you don't see. Which function has 1 over s Laplace transform? Nobody can see? Yes. So unity step. And I just did this previously, I don't want to repeat it. E minus t over tau. So this is the solution for the unit step. So let me plot this. So plotting that at t0, x of 0 gonna be 1 minus 1 gonna be 0. At t goes to a large value, x at large value gonna be 1 minus 0, 1. So if I plot it, t x, and this is the input to the system, unit step. One. The output gonna say, output gonna be this, as it says, 0 and 1. It's gonna be like this. Here we go. First order system. So the output x follows input. How much is the error signal? How much is the error signal is? Is 0. And mathematically, if you can prove it, it's gonna be limit s f of s 1 plus g when s gonna be limit of s. Laplace of step is, please mute your microphone speaker, please. 1 over, please mute, s goes to 0. Please mute your speaker, please. S, so gonna be limit of 1 over tau s plus 1 divided by tau s. S goes to 0. Tau s goes to numerator. Tau s plus 1. S goes to 0. 0. You see that? Very trivial mathematics prove everything. So, being said, if you are done, I will go to the Simulink. Can I? So, I want to, what the hell is this? Oh, this is another one that I copied, okay. So, I'm saying, no, I want to do it in the previous one. Impulse here. Okay, I'm just copying, pasting. What I'm doing here, because I want when you run this, you see the difference. So this was for the impulse, okay? And here, what you have to, I have to change it, because open loop transfer function is the original one, guys. Look at here, guys. Let me do this. Let me do this. X over f was 1 tau s plus 1. I'm not changing this, so the closed loop transfer function, as we did here, get here, is 1 over tau s. For the impulse, I change this. For the impulse, we change this, but for the step, we don't change it. It's 1 over tau s. Say tau is 2, huh? So it's gonna be tau is 2. It's gonna be 1 and 0 because 0 and 1, sorry, 0 and 1 because it's 1 over tau s, and 2 and 0 because tau is 2. Look at here, 1 over 2s. Open loop transfer function. So you see there's a huge difference, guys. If I wanted to plot the impulse input, I change the transfer function and it's open loop transfer function. But for the step, I don't need to change it. I'm just putting the G, 1 over 2s. See what I'm saying? Yes? Clear, everyone? So, and I'm gonna put the marks here now. And because I want this. And right click this to be compared with this. So for the stable first order systems, you see that here we go. This is input to the system step. This is output to system, goes to there. Stable first order system, guys. Obviously, if you copy paste, if you plot the E goes to 0. Here we go. Okay. So if I run this, E from 1 goes to 0. Error signal goes to 0. Clear, everybody? Yes? And I'm just putting here because I taught you previously this, because I'm gonna send this to you. If I change the time constant, see here, guys, I don't care about this, and I don't care about this, and I don't care about this. I'm changing the time constant to 5 seconds instead of 2. See, 5. I'm expecting the, see, 1 over 5. Now I'm gonna double click on this. You have 2 inputs to the marks. I'm putting 3. Here we go. Now I'm gonna plot this output as we did in mathematics to the input of this. If I save this, and if I say this is 30 seconds, save. Here we go. This is for time constant of 2 seconds, time constant of what? 5 seconds. It takes more time because you're increasing time constant, and this is the input. The same is valid if I copy, paste this here. And double click on 2. Okay. And if I error signal of this here, and the error signal of this to here, and the plot both. Okay. See that error signal goes to 0 because it's stable first order system. But see, this is for the 2 second time constant. This is for 5 second time constant. And error signal goes to 0. Clear, guys? Yep. I'm gonna send these and the code to you. And now we can